A-level mechanics, friction, the coefficient of friction. Let's have a look at how friction affects situations in mechanics. If an object rests on a horizontal surface, it will not move. In the diagram we see a mass m resting on such a surface. We can draw in the forces. There's the weight, mg, acting vertically downwards, and the normal reaction N acting vertically up. Even if it's pushed to one side by a gentle force, it's still very unlikely to move. A resistance force appears in the opposite direction that prevents it moving. This force is called friction and is exactly large enough to prevent motion. If the force pushing it to one side is increased, then the frictional force will also increase to prevent it moving. And this can go on. We can increase the applied force, and the frictional force will increase by exactly the same amount. However, the frictional force cannot increase indefinitely. Eventually, the applied force will overcome the frictional force, and the object will begin to slide across the surface. The frictional force has a maximum value, sometimes called F0. We can see this in the diagram as a pale blue arrow. The frictional force can be any size up to this maximum to prevent motion, but cannot get above the maximum. Once the object begins to slide, the frictional force does not disappear. It remains at its maximum value, F0, opposing the motion. The maximum value F0 of the frictional force depends on two things. The first is the nature of the two surfaces in contact, the object and the other surface. Some surfaces are naturally more slippery than others. Ice, for example, is very slippery, whereas rubber is not. The other thing that affects the maximum friction between two bodies is the size of the contact force between them. In other words, how hard they're being pushed together. In the diagram we see a block of mass m lying on a surface. If we mark in the forces, we've got a force mg, the weight, acting down, and then we have a normal reaction N. And I can draw in the maximum possible frictional force, called F0. Now in the second diagram, we've got two blocks of mass m, so the weight is now 2 mg. In diagram 1, we've got N equals mg, and in diagram 2, we've got N equals 2 mg. And that means the normal reaction in diagram 2 is twice the normal reaction in diagram 1. Now it turns out the maximum possible frictional force F0 in diagram 2 is twice F0 in diagram 1. So we get the maximum frictional force is proportional to the normal reaction. So we can write F0 is equal to mu n, where mu is the constant of proportionality. Now we call mu the coefficient of friction and use it as a measure of how slippery a surface is. A low value of mu means it's very slippery. A high value of mu means it's not slippery. To sum up, if F is a frictional force on an object from a surface, then F is less than or equal to mu n, where n is the normal reaction and mu is the coefficient of friction. If the object is on the point of sliding, or is actually sliding, then F is equal to mu n. If the object is on the point of sliding, it's called limiting equilibrium. Now we sometimes use F0 to represent the maximum possible friction. So F is always less than or equal to F0, where F0 is equal to mu n. Let's look at an example. A block of mass 4 kilograms lies stationary on a level plane with a coefficient of friction mu equals 0.3. There's a force of 28 newtons pulling it horizontally to the left. There is also a force P pulling it to the right. What are the possible values of P if the block does not move? Well, to solve this, we've got to consider two cases. Does it slip to the left or does it slip to the right? So in the first case, we'll assume the frictional force is to the left. On the diagram, we can mark in the forces. Now, P and the 28 newtons are already drawn in. We've also got the weight of the object, that's 4G acting vertically down, and we've got a normal reaction N acting vertically up. We've also got the frictional force F, which we've drawn to the left. Now, if we resolve vertically, we get N equals 4G. And assuming the object does not slide, then F is less than or equal to mu N. So F is less than or equal to 0.3 times 4 times 9.8. F is less than or equal to 11.76. If we resolve horizontally, we get F plus 28 is equal to P. In other words, P minus 28 is equal to F. Now we know F is less than or equal to 11.76, so P minus 28 is less than or equal to 11.76. And if we add 28 to both sides, P is less than or equal to 39.76. Now let's assume the frictional force acts to the right. We have the same diagram, but the frictional force has moved. Now, as before, F is less than or equal to 11.76, but if we resolve horizontally, F plus P is equal to 28. So 28 minus P is equal to F, which means 28 minus P is less than or equal to 11.76. If we add P to both sides and subtract 11.76 from both sides, we get P is greater or equal to 16.24. And so our answer is P lies between 16.24 and 39.76. In example 2, we're told a brick is in limiting equilibrium on a slope which makes an angle of 32 degrees with the horizontal. Find the coefficient of friction. Well, to solve this, we need to draw a diagram and mark in the forces. Let the mass of the brick be M. Then we can draw in the weight of the brick, mg acting vertically down, and the normal reaction N perpendicular to the plane. Now the frictional force acts up the plane. We can label that F. And then resolving up the plane, we see that the angle between the plane and the vertical is 58 degrees. So we have F equals mg cos 58. The component is always the cosine of the angle between the force and the direction we want. We can write this as F equals mg sine 32. If we now resolve perpendicularly to the plane, we get N equals mg cos 32. Now, using F equals mu N, we have mg sine 32 equals mu times mg cos 32. The mg's cancel and we're left with sine 32 equals mu cos 32. So mu is sine 32 over cos 32, which is tan 32, which is 0.6248. And so we have the coefficient of friction mu is equal to 0.625. In example 3, a brick of mass 1.2 kilograms lies on a flat surface. It's pulled along at a constant velocity by a string making an angle of 27 degrees to the horizontal. The tension in the string is 8 newtons. Find the coefficient of friction. To do this, we have to draw a diagram and mark in the forces. First we have the weight, that's 1.2 kilograms weight, or 1.2 G. Then there's a normal reaction vertically upwards, N, and there's a tension in the rope which is 8 newtons. And we have the friction, F. Now we've got F equals mu N. If we resolve horizontally, we get F equals 8 cos 27 degrees, which is equal to 7.12805. And if we resolve vertically, we get N plus 8 cos 63 degrees equals 1.2 G. So N is equal to 1.2 times 9.8 minus 8 cos 63, which works out to be 8.12807. Now we have mu is equal to F over N, which is equal to 7.12805 over 8.12807, which works out to be 0.87696. And so we have our answer is mu, the coefficient of friction, is equal to 0.877. Example 4. Objects A and B with masses 6 kg and 3 kg are attached to a light, inextensible string stretched over a smooth pulley. A rests on a rough table and B hangs freely over the edge. When released, each mass has an acceleration of 1.2 meters per second squared. Find the coefficient of friction between A and the table. Well, to solve this, the first thing we need to do is draw a diagram of A and mark in the forces. Now the mass of the object is 6 kilograms, so there'll be a weight of 6G. There'll also be a normal reaction acting vertically up. Now let the tension in the string be T, so there will be a force T to the right. And then there'll be a frictional force to the left. Now we know the mass has an acceleration of 1.2 meters per second squared. So, resolving horizontally and using F equals ma, we have T minus F equals 6 times 1.2, or F is equal to T minus 7.2. And if we resolve vertically, we have N equals 6G, so N equals 6 times 9.8, which is 58.8. Now we can draw a diagram of B and mark in the forces. Again, the first thing we can draw is the weight, which will be 3G, and there is a tension T vertically upwards. Now because the string is light and the pulley is smooth, the tension on B is the same as the tension on A. Also, we've got an acceleration, and again it's 1.2 meters per second squared. Resolving vertically using F equals ma, we have 3G minus T equals 3A, so 3 times 9.8, which is 29.4, minus T equals 3 times 1.2. We can rearrange that to give T equals 29.4 minus 3.6. In other words, T is 25.8. Now, if we substitute T in 1, we get F equals 25.8 minus 7.2, or F is equal to 18.6. But F equals mu n, so 18.6 equals mu times 58.8. That gives us mu is equal to 18.6 divided by 58.8, which works out to be 0.31632. And so we have the coefficient of friction mu is equal to 0.316. Example 5. A uniform ladder stands on rough ground and leans against a smooth wall at an angle of 64 degrees to the horizontal. If it's in limiting equilibrium, find the coefficient of friction between the ladder and the ground. Well, to solve this, draw the diagram and mark in the forces. Let the ladder have length L and mass m. We have the weight of the ladder, mg, acting vertically down halfway along the ladder. The ladder makes an angle of 26 degrees with the vertical. We also have a normal reaction N at the base of the ladder acting vertically up. We have a normal reaction R of the ladder against the wall acting horizontally, and this makes an angle of 64 degrees with the ladder. and we have a frictional force F at the base of the ladder acting along the ground. Now, if we resolve horizontally, we get F equals R, and if we resolve vertically, we get N equals mg. Remember, the turning moment of a force is the force times the distance from the pivot to the force times the sine of the angle between the distance and the force. So, taking moments about the base of the ladder, we have mg times L over 2 sine 26 degrees equals R times L sine 64 degrees. And this simplifies to mg sine 26 equals 2R sine 64. Now if we substitute 1 and 2 into 3, we get n sine 26 is 2f sine 64, or f over n equals sine 26 over 2 sine 64. But f over n is mu, so mu is sine 26 over 2 sine 64, which works out to be 0.24386. And so the coefficient of friction, mu, is equal to 0.244. Let's just have a look at a few notes on friction. Unlike topics such as Newton's second law with the formula F equals ma, the equations of motion, conservation of momentum, and many other things we've covered in mechanics, which are all as accurate as we can measure, the rules of friction are only approximate. If you place a book on a table and gradually tip the table up, you can measure the angle the table makes at the point where the book starts slipping, and then calculate the coefficient of friction from that. However, you're likely to get different answers each time. It is never possible to replicate the previous attempt exactly. Friction is caused by the roughnesses of the surfaces in contact. We can see this in the diagram. The ridges and grooves lock into one another. The surfaces may look smooth but be rough at the molecular level. If a liquid or moisture gets between the surfaces, it may force them apart, making it easier for the surfaces to slide. We can see this in the second diagram. Water can make a difference to the coefficient of friction. Wet roads are more slippery than dry roads. Oil or soap can dramatically reduce friction. In mechanics, we assume the coefficient of friction is independent of the contact area, and this is reasonably true. The rule, the friction is proportional to the normal reaction, is also reasonably accurate. In mechanics, we assume that there's a maximum friction an object can have before it starts sliding, and once the object starts sliding, the friction remains constant. In fact, it reduces, often by about 10%. The maximum frictional force an object can have before it starts sliding is called a static friction. The frictional force, once the object is moving, is called a dynamic friction. Similarly, we have a static coefficient of friction and a dynamic coefficient of friction. For all work at this level, we assume these two are the same. Although results from friction calculations are approximate, they're still very valuable. Police estimate car speeds in a crash from the length of the skid marks. Although the result may have a 10% error, it's still possible to tell if a car involved was travelling well in excess of the speed limit. Knowing the coefficient of friction in different materials, it's possible to choose the best materials for working parts of a machine.